right, so we're going to start by looking at figure out the magnetic field from a circular arc. So we're going to have some little part of a circle. Supposedly that's a circle. And we have a point here that is a distance r from it. All the points are a distance r from it. Kind of like a quarter circle, I guess, there. But it's not a great one. Okay. And I'd like to know, what is the magnetic field there? Well, if I look at that whole wire and I have a current, I'm going to say that in this case the current is going, get that going, okay, so we could go in counterclockwise along that little arc or whatever. If I point my thumb to the left and I grab onto that wire, at point B, I'm going to have a field that comes out of the page, and that's pretty easy to see. Okay, and that's going to tell me the direction, but it doesn't tell me the magnitude. So I'm going to have to go back to Biot-Savart to actually figure that out. And so I start here. dB equals mu naught I dl cross the radial unit vector divided by 4 pi r squared. All right. Well, that's a good start. You can see that all of the little segments of the wire, and let me choose a little segment, ds, the part where this is. We're going to call that ds. Okay. In that little segment ds, and in fact in every segment ds, because it's a circular arc, it's not just like a curved arc, it's a circular arc, that every segment is going to be perpendicular. So this angle is always going to be 90 degrees. I don't have to worry about doing a sign for it because it's always going to be the same. Okay. So I can go back to just writing that in. Okay. So and dl is going to be ds, and ds is going to be related to the angle of our arc. Okay. Because if I drop in, here's our little r. Okay. We know that that s, ds, if I call the angle phi in here, that's going to be the angle that makes up between the two ends of the arc, and our little segment, our little ds segment, the endpoints of our segment, and where they meet our point we're interested in. It's going to be r times that angle. Okay, it's the same as what we did when we looked at linear displacement versus angular displacement. We multiplied the two. So I can replace that. I can go back. Equals r. I guess I can call that d theta. Maybe that's better. Okay. So mu naught I. Whoops. Erase that. That's probably better too. Mu naught I r d phi divided by 4 pi r squared. Okay. So that's going to be the little contribution. And the r, that radius, is going to be the same as this one. So I can divide one of these out. Get rid of that. Okay. Now I have to add all of those for all the little bits of the segment to find out what b is. It's going to be the integral of r db. And that actually doesn't turn out too bad. Remember that the only real variable we have is this little angle here. That's the only thing that's going to change. Okay. R is a constant. It's the radius that we have. So this is just going to be mu naught I, and I'm going to call it just theta over 4 pi r. And again, this is the angle of the arc, but I want to point out it's in radians. Okay, so you have to actually measure in radians in order to make it work. Let's look at a couple of examples so we can get a feel for that. So the first example let's look at, the most common examples. Let's say we have a whole circle. So I have an entire circle with a radius of capital R. And I want to know, what is the magnetic field in the center of it? I've got a current, by the way, that goes, in this case, I'm going to make it clockwise, so it goes around the circle this way. I want to point out that the direction, because it goes clockwise, is going to be into the page this time. Okay, and I'm going to go back to using B equals mu naught I theta, or phi, sorry, over 4 pi r. Well, I got me a whole circle this time, so it's going to be mu naught I times 2 pi divided by 4 pi r. You can see the pi divides out, and we're going to end up with mu naught I over 2 r is going to be our magnetic field in the very center. And again, this time it's into the page because of the direction. The other most common example is a half circle. I've got some kind of wire here. And a half circle. It's got a current going through it. Sorry, current going through it this way of I. And what is the magnetic field here? And just like last time, if you take a look and you grab any segment of the wire, you're going to find that the direction is into the page. And we're going to use that same expression we used last time, that B equals mu naught I phi over 4 pi r. Oh, I'm sorry, I didn't point out what the radius was. Again, most times it'll just be capital R. So this time it's going to be exactly what it looks like, mu naught I. Again, we're just going around half the circle, so it'll just be pi over 4 pi r. So mu naught I over 4r, the pi's just divide out.